Have you ever stopped to truly appreciate human movement? Think about it for a second. The incredible speed of Usain Bolt, right? Topping out at nearly 28 miles per hour. Wow. Or the sheer explosive power needed for someone to jump over 4 feet straight up. It really is astonishing, this complex dance of muscle and bone and nerve. But what if those incredible feats are just the beginning of what's truly possible for movement itself? What if robots weren't just, mimicking human motion?
Yeah.
But we're about to create entirely new physical realities. Okay, let's unpack this. You sent us some fascinating material, particularly insights from Beyond Motion, how robots will redefine the art of movement by Paramendra Kumar Bhagat. And it really challenges our everyday understanding of robots, which, let's be honest, often feels stuck in maybe sci-fi movies from decades ago. So our mission with this deep dive is to explore a radically new philosophy of robotics. It's about seeing machines not just as tools, but as true movement artists, engineers, pioneers even. We're going to dive into how robots can transcend biological constraints, invent entirely new motion languages, and fundamentally expand human imagination. We want to invite you, the listener, to see a world where movement is completely redefined.
Yeah, and what's fascinating here is how this material encourages us to question the very definition of motion itself. What does it even mean for something to move? For centuries, our benchmarks for movement have been biological. How fast can we run? How high can we jump? But this source, it really pushes us to consider what happens when we unbind movement from those, well, biological assumptions. It just opens up an entirely new universe of possibilities. It really does.
Absolutely. And for such a long time, our vision of robots was really quite limited, wasn't it? It felt tethered to this singular, very human centric idea about make machines do what humans can do, from ancient myths featuring mechanical men to the industrial robots we see on factory floors today. The goal was often simple replacement. Could a robot walk like us, grasp like us, maybe even dance like us? We've pushed really hard to emulate human dexterity, balance, coordination, and to be fair, the results have been impressive in some ways. Humanoid robots can run now, they can lift heavy objects, even perform intricate surgeries.
But as the source points out quite sharply, even with all that progress, the most advanced humanoid robots often remain, well, pale imitations of the real thing. They can be slower, clumsier, and certainly less adaptive than a human being in complex, unpredictable environments. They get close sometimes, but they never quite match that organic fluidity of human motion.
Which makes me wonder then, was this whole copy the human paradigm just too small a vision? Was it like a cage we built from our own muscles and bones, limiting what robots could truly become?
That's a great way to put it. A cage built from muscles and bones. Humans are extraordinary, absolutely no argument there, but we are fundamentally limited by our biology. We tire, we stumble, we can't see in every direction at once. We certainly can't lift a ton without assistance, nor can we vibrate our fingers 1,000 times per second
Mhm.
or form perfect geometries while moving. And adapting our physical form mid-dance, yeah, forget about it. The real revolution, the source argues, begins when we free robots from these very human constraints and ask a deeper, more audacious question. What kinds of motion have never existed before, simply because biology couldn't permit them? Once you start asking that, the horizon for what's possible it truly explodes open.
It's a completely new framework then for understanding robotics. Instead of seeing them as just better humans, we start viewing them as, well, true movement artists, maybe, engineers and pioneers operating on a much broader physical canvas. The source outlines 3 core principles for this reimagined philosophy, right?
Exactly. The first one is to transcend biological constraints. This means designing robots for capabilities biology could never achieve, pushing beyond our limits in speed, precision, strength, adaptability. Imagine surgical microbots, tiny things operating simultaneously on hundreds of points inside the human body with superhuman steadiness, performing tasks with a precision far beyond any human hand. That's the idea. Or think about search and rescue robots that can morph into ladders or maybe coils to navigate disaster zones where a human body just physically couldn't go. The core insight here isn't just about bettering human action, it's enabling actions that really defy our biological imagination.
Okay, that makes sense. And that leads directly to the second principle you mentioned.
Yes, inventing new motion languages. Just as we have ballet, hip-hop, or salsa, different ways humans move expressively or functionally, robots can create entirely new ways of moving. Think about something called fractal motion, where a robot replicates movement patterns on multiple scales at the same time, creating these intricate, self-similar designs purely through motion. Or swarm choreography, where hundreds, maybe thousands of robots coordinate to form living, moving sculptures, swirling and shifting with incredible fluidity. This vision truly transforms roboticists, doesn't it? From mere engineers into, well, choreographers, composers, directors of kinetic imagination.
Choreographers of kinetic imagination. I like that.
And this invention of new motion languages naturally expands into the third principle, expanding human imagination. The analogy the source uses is really powerful. It says, when the Wright brothers first flew, they didn't create a better horse. They invented an entirely new relationship between humans and the sky.
Right. A whole new dimension.
Precisely. In the same way, robotic movement, freed from biological limits, could redefine architecture, giving us buildings that breathe, maybe, or expand or shift based on needs. It could revolutionize sports with new hyperdynamic games where humans and robots interact in entirely new ways, or enrich entertainment with stages that literally move and evolve with the performance. The possibilities just become endless.
So robots become much more than just labor-saving devices in this view. They become dream makers. They could be artists creating movement poetry beyond our physical limbs. They could be builders assembling structures we once thought unimaginable, or explorers navigating spaces where no biological body could survive. Or even companions, maybe, sharing experiences through dynamic, perhaps even emotional movement.
Exactly. Every new movement made possible by robotics isn't just a technical feat. It's really a step into a larger universe of human imagination. So ultimately, the new ethos of robotics means retiring that, well, small dream of robots as just metal humans. Instead, we embrace a future where robots don't just walk like us, they move beyond us. They invent new forms of expression, exploration, and excellence.
And critically, they won't be limited by human imagination. They'll expand it.
That's the core idea. The future of robotics isn't in better imitations, it's in bolder creations.
Okay, so to truly grasp that, we probably need to understand what those human limits actually are. When we talk about human movement, it's easy to just get lost in the sheer marvel of what our bodies can do. I mean, from the incredible dexterity of a neurosurgeon's hands to the explosive power of a weightlifter, our muscles, bones, tendons, they work in this really elegant harmony to produce a vast repertoire of motions.
And it's crucial to acknowledge that. Absolutely. Understanding where human movement reaches its limits isn't about diminishing human achievement at all. It's more about recognizing the very specific biological constraints that bind us. And by understanding them, we can actually identify the space where robots can begin to innovate, to go beyond what we can possibly do. It's almost an act of reverence for our own biology. It allows us to see where a new chapter can begin.
Okay, that's a good way to frame it. So let's break down these biological constraints. First, you've got muscular constraints, right?
Our muscles are organic marvels. Sure, they produce force, but they're bound by a specific power-to-weight ratio. They can only produce so much force relative to their size and mass. Their contraction speed is finite, limiting how fast we can move. They generate heat, which leads to overheating issues. And crucially, they fatigue. They accumulate metabolic waste like lactic acid. This is why even an elite athlete like Usain Bolt can only sprint at top speed for, a few seconds before inevitably slowing down.
Right. And then there are the bones, skeletal constraints.
Yeah, our bones provide structure, but they're not indestructible. There are material limits to how much force bone can withstand before fracturing. Our joints have a finite range of motion, and as many of us know, they're prone to wear and tear over time. Our skeletons can only support a limited amount of weight without injury. Certain extreme load-bearing tasks are just. They're outside the scope of human capability without significant mechanical assistance.
And we can't forget gravity, that constant, ever-present force.
Absolutely defines how we move. It's why the maximum vertical jump for a human is only about, 1.2 meters, 4 feet or so? Gravity relentlessly pulls us back down. Fighting against it is incredibly energy-intensive, limiting how high or far we can move vertically. Humans essentially evolved to work with gravity, mostly not against it, and that imposes fundamental restrictions on certain types of motion.
Okay, and finally, fatigue and endurance, the universal limits.
Universal human limitations, yeah. No matter how strong or skilled you are, fatigue is inevitable. Our bodies store a limited amount of readily accessible energy, like glycogen. And aerobic metabolism needs a continuous supply of oxygen, which caps our endurance. And beyond the purely physical, there's psychological fatigue. That can degrade motor skills and reaction time long before our muscles actually give out. This is why even the greatest marathon runners, who seem tireless, must eventually stop and recover.
So when we look at elite human performance, we can really see where we hit these natural ceilings. Like you said, the fastest human sprint is around 27.8 miles per hour. The heaviest deadlift may be just over 1,100 pounds, even for endurance. Marathoners can run for hours, maybe even days in ultra events, but they still require careful pacing and sustained fueling. Energy stores and muscle breakdown impose these upper limits.
And precision, too. Neurosurgeons demonstrate incredible motor control, sure, but even the steadiest human hand has a baseline tremor. It just does. The finest precision we can typically achieve is in the order of millimeters, maybe tenths of millimeters, not micrometers or nanometers. Multitasking and coordination are similar. Juggling 7 balls is amazing, right? But juggling 70 is, well, biologically impossible for us. And recovery from serious injury or just extreme fatigue is slow, often incomplete, and sometimes the damage is permanent.
But this is exactly where robots begin to shine, isn't it? While we hit these ceilings, robots can start from entirely different premises.
Exactly. They can have, for instance, essentially infinite endurance, operating continuously 247 with only minimal pauses for maintenance or power.
They can achieve superhuman speed.
Yeah, with electromechanical systems that execute movements far faster than human reflexes, performing thousands of precise operations per minute, potentially without error.
And superhuman strength?
Definitely. Able to lift, push, pull, manipulate objects far heavier than anything a human could handle, and with much greater consistency and safety protocols built in.
Plus that ultra precision you mentioned.
Remarkable, operating at micron or even nanometer levels. Think of those microsurgical bots making incisions or repairs literally invisible to the human eye. Or assembly robots fitting microscopic components with perfect repeatability, time after time.
And where human attention is limited, robots can demonstrate multitasking mastery.
Right. A single robot could, hypothetically, operate multiple tools at once, monitor different data streams simultaneously, and adjust its processes dynamically, managing dozens or even hundreds of simultaneous tasks in ways we just can't.
And perhaps most excitingly, this idea of morphology and adaptability.
Yeah, that's a big one. Unlike our fixed human bodies, robotic bodies can be designed to change shape. They could extend, contract, fly, swim, climb. Modular robots can even reconfigure themselves mid-mission, swapping parts or changing form, a capability completely foreign to biological organisms.
So the philosophical implication here, according to the source, is that the goal isn't just to catch up to us.
Not at all. It's to leap beyond. To invent motion paradigms completely unbound by biology. Think about it historically. Boats didn't just imitate swimming better, they floated using buoyancy. Airplanes didn't just flap wings harder. They achieved sustained flight through entirely new principles of aerodynamics and propulsion. Satellites don't jump into orbit. They escape Earth's gravity through calculated propulsion and orbital mechanics.
So robots shouldn't just walk like humans.
Exactly. They should aim to create entirely new relationships between energy, matter, and motion. Understanding our own biological limits isn't a defeatist exercise. The source frames it as an act of reverence. By mapping the boundaries of human physicality, we honor our species' extraordinary achievements, yes, but at the same time, we lay the groundwork for a whole world of new possibilities.
That's a powerful way to put it. Robots have the opportunity to pick up where biology leaves off. They can sprint faster, lift heavier, endure longer, operate with that surgical precision. But maybe more importantly, they can invent types of movement we have literally never seen before, inspiring new dreams, new industries, new experiences. Okay, let's talk about movement unbound by maybe direction or anatomy. Our human movement, while it can be graceful, is largely constrained by our anatomy, right? We move in primarily linear or rotational ways, confined by our joints, muscle arrangements, and that ever-present pull of gravity. But robots, as we're learning, they aren't tethered to these biological forms. They can seamlessly combine wheels, arms, tentacles, wings, propellers, and maybe completely novel movement systems we haven't even thought of yet.
Exactly. And this ability to combine and coordinate across multiple vectors of motion simultaneously.
Yeah.
It isn't just an enhancement of human capability. It's really a total reimagining of what movement can be.
So vectors. Just to remind everyone, that's about magnitude and direction.
Right. In physics, a vector represents both magnitude, how much, and direction, which way. Traditional human movement tends to focus on relatively simple, maybe one- or two-dimensional vector control, walking forward, jumping up, turning side to side. Robotic systems, however, can integrate and execute multiple vectors simultaneously. Think translational motion, moving along X, Y, or Z axis, rotational motion, spinning around an axis, oscillatory motion like vibrations, and incredibly complex combined motions. They can control and optimize all of these at once, creating these layered, sophisticated movement strategies that are just beyond us.
Okay, can you give us some examples to make it more concrete?
Sure, let's start with something familiar, like robotic arms. We see them in factories. They often boast 6 or more degrees of freedom, allowing rotation and translation along multiple axes simultaneously. And they do it with hyper-precision, measured often in microns, millionths of a meter. Think of those automotive assembly lines where multiple robotic arms are simultaneously welding and bolting parts onto a car frame. They move with this synchronized precision, executing trajectories that would be utterly impossible, not to mention dangerous, for human workers.
Okay, arms make sense. What about tentacles? That sounds more exotic.
It does. Robotic tentacles often mimic the flexibility of octopus limbs, but enhance it with advanced material science and AI control. They can offer potentially infinite degrees of freedom, bending, twisting, wrapping around objects in complex ways. They can even adjust their stiffness, going from soft and compliant to rigid and firm, depending on the task. This makes them ideal for, say, delicate object manipulation. Imagine an underwater exploration robot reaching into the tight, fragile spaces of a coral reef, handling delicate samples without causing damage.
That's incredible. And wheels. They seem pretty basic compared to tentacles.
They might seem basic, but robotic systems elevate them significantly. Sure, they provide high-speed travel and stability on flat surfaces, but increasingly we see robots using omnidirectional motion with specialized wheels, like mecanum wheels. Those are the ones with the little rollers angled around the circumference.
Ah, yeah, I've seen those. They can slide sideways.
Exactly. They allow the robot to move laterally, diagonally, or spin in place without actually turning its body. In a warehouse, these robots can zip across floors, navigate tight aisles, pick and transport goods with incredible efficiency, especially in crowded spaces.
And for true three-dimensional freedom.
And you need propellers, usually. Propeller-based systems like drones, quadcopters, they enable vertical lift, hovering, rapid directional changes, true 3D movement. Drones can inspect bridges or skyscrapers from angles completely inaccessible to humans, hovering precisely, spinning, zooming in any direction they need to.
But the real breakthrough you're saying is when they combine these.
That's where it gets really interesting. Creating hybrid robots. Imagine a robot designed for disaster response. Maybe you could fly into a disaster zone using propellers.
Okay.
Then land amidst the rubble, perhaps using legs or adaptable tracks to crawl through tight spaces.
Right.
And then use a powerful robotic arm to lift debris, all in one continuous adaptable operation. Or think about wheel-legged robots that can roll quickly on flat ground but then deploy legs to step over obstacles or climb stairs. This capacity for multi-vector, multimodal motion fundamentally redefines what lifelike or dynamic even means in robotics. It really challenges our understanding of what machines are capable of, and it definitely blurs the line between the mechanical and the, well, maybe the organic.
Okay, so beyond moving in multiple directions, you mentioned robots mastering precision across extreme scales.
Right.
From the microscopic to the colossal.
Yes, that's another area where they diverge dramatically from biology. In the natural world, very few creatures, if any, can effectively operate at both ends of the scale spectrum. An ant lifts many times its body weight, which is amazing, but it remains tiny. An elephant moves mountains of material, relatively speaking, but with comparatively slow, less precise movements.
And humans, we've extended our reach with tools, obviously, but we can't manually manipulate individual atoms, nor can we single-handedly hoist a building.
Exactly. But robots offer the possibility of mastering both micro and macro movements, achieving feats of precision and power that are simply unimaginable for biological entities. And this dual mastery is really ushering in a new era of innovation across countless fields.
So let's start small. With microscopic mastery, medicine seems like a key area here.
Absolutely. Medicine often demands a level of precision that's beyond even the most skilled human hands, tremor being a factor. We're seeing the development of surgical microbots, potentially things like nanobots, designed to navigate the bloodstream to deliver drugs directly to cancer cells or repair tissues at a cellular level. There are microsurgical arms being developed that could perform operations on individual nerves or tiny blood vessels, and tiny endoscopic robots that can traverse the body's internal cavities, sending back images and maybe even taking biopsies with incredibly high precision. The potential benefits are huge, reducing complications, minimizing invasiveness, accelerating recovery times.
And this microscale precision extends beyond medicine, right, into manufacturing.
Oh, definitely, especially in electronics and high-tech manufacturing. Think about semiconductor manufacturing. Robots with micromanipulators assemble components that are literally invisible to the naked eye. They position and bond these components with nanometer precision. A misalignment of even a few microns could mean device failure. That's the level we're talking about. Same goes for assembling tiny lenses for optical devices or fabricating complex medical devices like stents or pacemakers. It demands robotic precision.
Okay, so that's the micro end. What about the other extreme, macro mastery?
Here we're talking about robots designed for sheer brute strength, scale, and durability. Think of those giant, heavy lifting robots, the massive robotic cranes you see at ports, loading and unloading shipping containers weighing many tons, often doing it with surprising speed and accuracy. Or construction robots that can automatically lay bricks, pour concrete over large areas, or even 3D print entire structures layer by layer. In mining, specialized robots can move tons of earth and rock with minimal human oversight, operating in dangerous environments and reshaping industries dependent on heavy materials.
And this also applies to building really big things, infrastructure assembly.
Yes, absolutely. Robotic systems are increasingly used to build bridges, tunnels, and skyscrapers. We're talking about robotic bridge builders that can position and secure massive segments of bridge infrastructure with minimal direct human labor. Or those gigantic tunnel boring machines, TBMs, that carve through mountains and under cities, essentially large-scale robotic systems. There's even work using prefabricated modular robots to assemble entire rooms or even floors of buildings in rapid succession. The advantages are significant. Increased safety for workers, potentially reduced costs, and often much faster project completion times.
But what's truly revolutionary, you mentioned, is robots bridging the micro and macro, doing both.
That's where some of the most exciting developments are. Robots designed for adaptive scaling, shifting between fine motor skills and gross motor skills as needed. A surgical system, for instance, might use large gross arm movements to position itself correctly over the patient, and then switch to incredibly fine-scale movements, maybe using micro tools at the tip, to perform delicate suturing with micron-level precision. Or think of a construction robot positioning a massive steel beam weighing several tons, but doing so with millimeter-level accuracy to ensure structural integrity.
And you also mentioned modular systems.
Right, modular robotic systems that can assemble themselves into larger structures for heavy lifting tasks. Or, conversely, break apart into smaller coordinated swarms to perform fine detail tasks, like inspection or cleaning in complex environments. This adaptability opens up entirely new possibilities for exploration, manufacturing, disaster recovery, you name it.
So this capacity really redefines human capability then.
It absolutely does. Tasks that were once considered impossible or just wildly impractical are now becoming achievable. Everything from potentially designing new molecules atom by atom using micromanipulation, all the way up to building entire cities, perhaps even on Mars someday, using macro-scale construction robots. Robots, in this sense, become not just tools, but powerful extensions of human will and ingenuity across dimensions previously completely out of reach.
Okay, so we've talked about direction and scale. Now, what about form itself? Traditionally, when we think of machines, we imagine these rigid structures, right? Designed for specific tasks with fixed forms. A cart is a car, a crane is a crane. But what if machines could fed those fixed forms entirely? What if they could stretch, compress, fold, maybe even flow like liquid, adapting their shapes in real time?
That's the really mind-bending essence of morphing machines. Robots that aren't bound by singular static structures, but are capable of dynamic shape-shifting, embodying the kind of fluid adaptability we sometimes see in nature, but perhaps taking it even further. This vision fundamentally transforms our understanding of what robots are and what they could potentially do.
How does that even work? What's the science behind a shape-shifting robot?
It starts often at the material level, with the development of smart materials. Things like shape memory alloys, SMAs, metals that can be deformed, but will remember their original shape and return to it when heated.
Okay, I've heard of those.
Or electroactive polymers, EAPs, plastics that physically bend, expand, or contract when you apply an electrical voltage to them. These materials allow bodies to transform without needing traditional motors, gears, and rigid frames. Another approach is modular robotics, which we touched on earlier, constructing machines from numerous smaller, simpler modules that can rearrange themselves. Think of concepts like self-assembling cubes that click together magnetically or mechanically to reconfigure into different structures, maybe a snake, then a wheel, then a bridge. Or swarm robotics, where large collections of micro-robots coordinate their positions to collectively form larger functional shapes.
And what about softer approaches?
That's a huge area too. Inflatable and soft robotics. Inflatable structures can rapidly change their volume and shape using pneumatic networks, basically, channels filled with air or fluid that cause flexible materials to bend and move when pressurized. There are also origami-inspired designs, where complex folding patterns embedded in flat materials allow them to pop up or collapse into intricate three-dimensional structures on command. The focus here is often on flexibility and compliance over sheer strength, creating machines that are inherently more resilient, adaptable, and safer for interacting with humans in complex environments.
So how does this morphing look in action? Can you give examples of stretching or folding?
Sure, we see concepts for stretching robots that could expand dramatically. Maybe for space exploration, like deployable solar sails or antennas that unfurl from a compact package, or in medical devices like stents that are inserted in a compressed form and then expand inside a blood vessel to open it up. In rescue scenarios, a robot might need to slip through a narrow gap and then expand on the other side to stabilize a structure or lift debris.
And folding, like
Wow.
robot origami.
Pretty much. Folding robots, often explicitly inspired by origami, use predefined crease patterns to shift between vastly different forms. Imagine deployable emergency shelters that start as flat packs and then automatically unfold into habitable spaces, or medical robots that can be swallowed or inserted in a folded state and then unfold inside the body to perform surgery or deliver medication. Even dynamic stagecraft in theaters where sets or props could dramatically fold and unfold live on stage.
The applications sound huge. Architecture, you mentioned.
Yes, the potential impact on architecture is fascinating. Imagine dynamic buildings with adaptive facades, walls, or windows that adjust their shape or transparency to control sunlight, temperature, or airflow. Or reconfigurable interiors where rooms can change size and function on demand. An office becomes a bedroom, a wall slides away to create an open space. Urban flexibility could even be possible, with streets that expand during peak hours, parks that reconfigure for events, maybe even buildings that can heal minor damage themselves using morphing materials.
And for emergency rescue.
It's a natural fit. Morphing robots could slip through tiny cracks in rubble to locate survivors after an earthquake. They could potentially expand to lift heavy debris, or adapt their shape to traverse unstable terrain, maybe flowing over obstacles instead of climbing. In medical emergencies, minimally invasive devices could adjust dynamically once inside the body, adapting to the patient's specific anatomy.
And entertainment seems like a playground for this.
Absolutely. Dynamic stagecraft, like we mentioned, allowing theater sets to shift and flow with the story in ways never possible before. Robotic performers, maybe dancers that literally change shape mid-performance, or puppets that reconfigure themselves. Theme parks could use morphing technology for responsive environments, or rides that physically transform during the experience.
That's quite a shift in perspective, isn't it? To think of a building not as static, but as something that can breathe and change.
It really is.
Yeah.
The philosophical implication in the source notes is that the very concept of a static object is fundamentally challenged. In a world of potentially fluid, adaptable forms, maybe objects become defined more by their function or behavior rather than their fixed shape. Spaces become dynamic participants in human experience, not just passive containers. And machines could become more like partners in shaping our environment, not just tools within it. It demands completely new thinking in design, engineering, certainly ethics, and even aesthetics. What does a beautiful morphing building look like?
Okay, from single morphing machines to collections. You mentioned swarms earlier. Let's dive into swarms and symphonies.
Right. This is about distributed intelligence in motion. And the inspiration is everywhere in nature, isn't it? Flocks of birds wheeling across the sky in perfect unison. Schools of fish darting and turning as one. Ant colonies building intricate nests or foraging efficiently, all without a single leader telling everyone what to do.
Right, there's no head bird directing the flock.
Exactly. This emergent intelligence arises from the collective actions of many relatively simple individuals, each following basic rules based on their local environment and neighbors. And robotics is now on the cusp of replicating, and maybe even surpassing, these natural phenomena. Through distributed intelligence, dozens, hundreds, or potentially even thousands of small, often simple robots are beginning to coordinate seamlessly, moving together almost like a single living organism. Swarm robotics opens up a completely new frontier of motion, with truly extraordinary possibilities across logistics, search and rescue, agriculture, environmental monitoring, and yes, even art.
So what are the core principles? How do they work without a leader?
The foundations of swarm robotics draw inspiration directly from biology, as I said. Key principles include local interaction. Each robot typically only senses and responds to its immediate neighbors, not the entire swarm state. Simple rules. Individual robot behavior is governed by a small set of basic rules like maintain a certain distance, match velocity, avoid collision. Complex group behavior emerges from these simple interactions. Decentralization. Critically, there's no single point of control or failure. Intelligence and decision-making are distributed throughout the swarm. This leads to robustness. The swarm can often tolerate the failure or loss of individual robots without collapsing, and scalability. In theory, you can add more robots to the swarm, increasing its capabilities without needing fundamental reprogramming of the core rules.
How do they communicate or coordinate then, if it's all local?
Various ways. It can be through proximity sensors detecting how close neighbors are. Wireless networking allows for more explicit data sharing, but often kept local. Sometimes it's through visual cues, robots recognizing patterns or lights on others, or even by modifying the environment, like ants leaving pheromone trails. Robots might leave virtual markers or change the physical space slightly for others to detect.
Okay, so where are we seeing this in action already?
Well, a big one is logistics and warehousing. Companies like Amazon famously use thousands of autonomous mobile robots, AMRs, in their fulfillment centers. These robots coordinate their movements using swarm principles to efficiently transport shelves of goods, avoid collisions, dynamically reallocate tasks, and self-organize routes to maximize throughput.
Right, I've seen videos about it. It looks like chaos, but it's choreographed.
Exactly. For search and rescue, swarms could revolutionize efforts in disaster zones. Imagine drone swarms flying autonomously over a collapsed building, cooperatively mapping the debris field in 3D. Simultaneously, ground swarms of small, perhaps insect-like robots could infiltrate the rubble, searching tight spaces too dangerous or inaccessible for humans or larger robots, sharing sensor data as they go. Their behavior could adapt based on what the collective finds.
And the source mentions military applications.
It does, and it's an area seeing rapid development. Applications include warfare and defense. This could involve swarms of surveillance drones operating cooperatively to monitor large areas persistently, or concepts like swarm attacks designed to overwhelm enemy defenses through sheer numbers, even decoy swarms to confuse adversaries. Now, it's important to reiterate, as the source material presents these capabilities, our role here is just to impartially report on them, to understand their potential capabilities and impact, not to endorse any particular use. The technology itself is powerful.
Understood. What about less destructive uses? Agriculture.
Yes, agriculture and environmental monitoring are promising areas. Fleets of small autonomous drones could collectively monitor vast areas of farmland, gathering detailed data on crop health, soil moisture, or pest infestations, allowing for much more targeted interventions. There's even research into using tiny robotic drones for artificial pollination, perhaps assisting where natural bee populations are declining, or swarms monitoring ocean currents or pollution levels.
And you mentioned art. How do swarms become art?
It's becoming a fascinating medium. Artists and creative technologists are using robotic swarms to create dynamic, interactive experiences. The most well-known example is probably drone light shows, where hundreds, sometimes thousands, of synchronized drones equipped with LEDs perform incredibly intricate aerial ballets in the night sky, forming complex shapes and animations.
Yeah, those are amazing to watch.
They really are. You also see interactive art exhibits where swarms of small robots on the ground or walls might respond to the movement or presence of the audience, creating these living, shifting sculptures. Robots are being explored as collective performers, dancers, musicians, even storytellers, where the swarm itself is the artistic medium.
What technologies are making this possible now?
Several key things are converging. Advances in AI and machine learning are crucial, allowing swarms to learn, adapt, and optimize their collective behaviors over time. Miniaturization and cost reduction, especially through MEMS, microelectromechanical systems, technology that's the engineering that lets us build tiny sensors, actuators, and processors, very cheaply makes deploying large numbers of robots economically feasible. Energy management is getting better, with more efficient components, onboard solar charging, or even energy sharing strategies within the swarm. And robust communication networks, like mesh networks where robots relay signals for each other, are vital for coordination, especially in complex environments where direct communication might be blocked.
It sounds incredible, but surely there are challenges.
Oh, absolutely. Huge engineering challenges remain. Coordination complexity is one ensuring hundreds or thousands of robots move cohesively without collisions, especially at high speeds or in tight spaces, is incredibly difficult.
Failure management is another. While robust, how does the swarm detect, diagnose, and compensate for failing units? Can they self-repair or effectively isolate faulty members? Scalability itself is hard. Rules that work for 10 robots might break down for 10,000. And security is a major concern. How do you prevent malicious actors from hacking or taking control of a swarm?
And beyond the technical, there are ethical considerations.
Big ones. The source raises several key philosophical and ethical questions. Autonomy. How much decision-making power should we give to swarms, especially in critical situations like defense or rescue? Can a swarm make truly ethical choices? Accountability. If a swarm causes harm, who is responsible? The programmer, the manufacturer, the owner. The swarm itself, it's murky. Privacy. Mass deployment of sensor-equipped swarms raises obvious surveillance concerns. And in warfare, the use of autonomous swarms raises deep questions about dehumanized combat and the potential for rapid, uncontrollable escalation.
So where's this heading? What's the future for swarms?
The horizons are pretty vast. Concepts include megaswarms, potentially millions of nanorobots working together for tasks like building massive structures in space, or even environmental remediation on a planetary scale. We'll likely see more human-swarm collaboration, where humans guide or interact with swarms in real time for complex tasks. There's research into biohybrid swarms, combining living organisms, like insects, with robotic components, and perhaps even emotional or aesthetic swarms imagine living architecture that responds to inhabitants' moods, or swarms designed purely for expressive communication or artistic beauty. Swarms really represent more than just a technological advance. The source suggests they herald a new way of thinking about agency, intelligence, and collective action itself. A kind of new mind, body, and maybe even spirit emerging from the many.
Okay, so we've gone from individual robots morphing to collective swarms. What about moving truly freely in 3 dimensions? Humans, as we've said, have largely been confined to 2-dimensional surfaces for movement. We walk, run, drive on flat planes mostly. Even our most ambitious leaps, like airplanes and submarines, still rely heavily on surfaces or principles like lift and buoyancy, often tied to gravity-bound constructs. But with robots, you're saying the dream of seamless, unbounded, true 3D mobility is actually materializing.
That's right. Robots are genuinely learning to fly, glide, swim, and even crawl effectively on walls and ceilings, moving through space with a freedom that biology rarely, if ever, allows. The limitations of our typical 2D mobility are pretty significant when you think about it. Ground movement is subject to friction, physical obstacles, path dependency, you have to go around things. And gravity's constant pull anchors us, limiting vertical exploration and ending constant energy expenditure just to overcome it. Robots designed for true 3D movement have to cleverly exploit or contend with these forces in new ways, rather than just being chained by them like we often are.
So what are the different modes of this true 3D robotic mobility? Flying seems obvious.
Yes, flying robots are a major category. Quadcopters, fixed-wing drones, more complex VTOL call, vertical takeoff and landing hybrids, they all break entirely free from surface constraints. Their applications are already widespread.
Right.
Aerial surveying and mapping, package delivery is starting, infrastructure inspection, bridges, power lines, wind turbines, cinematography, offering speed, reach, and perspectives inaccessible to ground-based machines.
Okay. What else besides flying?
Well, there are gliding robots. These harness aerodynamic forces, often without continuous propulsion, to travel efficiently. Think of glider drones released from a high altitude that can silently cover large distances using wind currents or dynamic soaring techniques, mimicking birds like albatrosses. These are great for long-duration missions like wildlife monitoring or potentially covert surveillance, where noise and energy consumption are critical factors.
In underwater.
Swimming robots open up the vast aquatic world, which is inherently a rich three-dimensional environment. We have underwater drones, remotely operated vehicles, ROVs, tethered to the surface, or autonomous underwater vehicles, AUVs, that operate independently. There are also developments in biomimetic swimmers inspired by fish or turtles, using fins or undulating bodies for propulsion, and mini-submersibles exploring the deep ocean. Applications range from marine research and archaeology to offshore oil and gas pipeline inspection or naval operations.
And you mentioned wall crawling. That sounds tricky.
It is. But wall-crawling robots are fascinating because they can transcend traditional horizontal planes even while technically remaining surface-bound. They use various clever techniques: gecko-inspired adhesion using microscopic hairs that create van der Waals forces, suction-based systems using vacuum cups, magnetic adhesion for ferrous surfaces, or even microspine gripping where tiny hooks engage with surface irregularities.
Wow, so they can climb walls or even walk on ceilings.
Potentially, yes. This enables them to do things like inspect the exterior of buildings or aircraft, operate inside complex machinery or spacecraft, or navigate through disaster zones with highly cluttered, multi-level environments.
What breakthroughs are making all this 3D mobility possible now?
It's a combination of things. Advanced propulsion systems are key, more efficient motors, ducted fans, maybe even experimental thrusters like ion drives or electrohydrodynamic (EHD) thrusters for specific applications. Lightweight yet high-strength materials are crucial, like carbon fiber composites, allowing for strong structures that don't weigh much, which is vital for flight and climbing. Sophisticated sensor fusion and AI control are absolutely essential. Robots need to integrate data from multiple sensors like cameras, LiDAR, inertial measurement units, IMUs, those tiny sensors that track orientation and acceleration, GPS to build a real-time 3D map of their surroundings and navigate autonomously and safely within it. Predictive algorithms help anticipate movement and avoid collisions. And energy innovations, higher density batteries, more efficient power management, maybe even energy harvesting techniques like solar power for drones are needed to extend operational times.
The philosophical implication here you mentioned is changing how we even think about moving.
Right. When movement is truly freed from surfaces, it changes how we conceptualize navigation itself. It's no longer just about following paths on a map. It becomes fully volumetric movement through space. Our cities, our homes, our workplaces could potentially become three-dimensional interaction spaces in new ways. Think drone delivery ports on buildings or robots climbing walls for maintenance. It changes our aesthetics, too. The beauty isn't just in the path, but in how the entire volume of space is utilized and sculpted by movement. Robots become true kinetic artists, shaping space itself.
But the future of robotics, the source suggests, is also moving beyond the mechanical entirely, beyond physical bodies touching things.
Yes, this is perhaps one of the most radical shifts in vision. When most of us think of robots, we still imagine mechanical bodies with joints, grippers, limbs. But what if future robots could manipulate matter without any direct physical contact, using forces transmitted invisibly through fields? This is the fascinating, almost sci-fi frontier of invisible motion, a world where force is exerted through non-mechanical means, enabling possibilities that seem almost magical.
So these future robots might not even look like robots.
Exactly. They might be systems that generate fields, flows, pulses. The robot might be the system controlling the field, rather than a physical entity moving within it. It's a paradigm shift. Take acoustic levitation, for example. This uses precisely controlled sound waves, often ultrasound, beyond human hearing to suspend and manipulate small objects in midair.
Suspend things with sound. How?
By creating standing sound waves. These waves have points of high pressure and low pressure, nodes and antinodes. If you shape the sound field carefully, you can create stable low-pressure zones where the acoustic pressure forces effectively counteract gravity, trapping a small object there.
Wow. So you can literally float things.
Yes, small particles, droplets, even tiny components. Applications could include handling delicate materials without contamination, biological research, manipulating cells, or even contactless assembly lines in manufacturing where sound moves parts into place.
And acoustic tractor beams.
That's the next step, not just levitating, but actively moving objects by shaping the sound field dynamically, pulling objects towards the sound source, or pushing them along complex paths. There's serious research into using focused ultrasound beams to non-invasively guide microrobots or drug delivery capsules inside the human body. Sound becomes not just a medium of communication, but potentially a tool for construction and motion at micro scales.
Okay, sound. What about magnetism?
Magnetic motion is another powerful non-contact force. By generating and carefully shaping magnetic fields, often using electromagnets, robots can move metallic or magnetically susceptible objects remotely. This is already used in some industrial lifting applications, research labs, and explored for things like guiding pill-sized camera robots through the digestive tract, or potentially for delicate spacecraft docking maneuvers. Magnetism also enables novel forms of magnetic swarms or modular robotics, where magnetically linked modules could potentially break apart, flow through constrained spaces, and then reassemble themselves on the other side, making motion incredibly fluid and adaptive.
And light. Can light move things?
It can. This is often called photonic manipulation. The best-known example is optical tweezers. These use a highly focused laser beam to trap and manipulate microscopic objects, things as small as viruses, bacteria, living cells, DNA strands, even individual molecules.
How does a laser beam trap something?
It's due to radiation pressure. Light exerts a tiny force. When a laser is tightly focused, the forces created by the light intensity gradient can trap a small particle at the focal point. By moving the laser beam, you move the trapped particle. This is a revolutionary tool in biology and nanotechnology, allowing scientists to directly manipulate the building blocks of life or assemble structures atom by atom. Light becomes a construction tool at the tiniest scales.
So sound, magnetism, light. This leads to the concept of robots without bodies.
Exactly, where the fields themselves effectively become the actuators, the things doing the work. The traditional notion of a robot as a discrete mechanical body starts to dissolve. Instead, the robot becomes a distributed system, maybe a volume of influence created by carefully controlled fields. Intelligence is embedded in the field generators and the control systems. You could imagine environmental robotics, where smart homes might reconfigure furniture using magnetic levitation or acoustic manipulation. Hospitals could have floating medical devices guided by fields. Factories might assemble products in mid-air using orchestrated light, sound, and magnetic fields.
Motion becomes ambient, pervasive.
Exactly. Seamless, silent, maybe even invisible. This truly defines a new paradigm of motion. It challenges our deepest assumptions about machines, action, and force. The future of robotics, in this vision, becomes increasingly integrated into our environment, perhaps less about distinct objects and more about intelligent, responsive spaces. Motion itself becomes an invisible art, woven into the very fabric of our lives.
Okay, so we've explored all these incredible possibilities for robotic motion speed, precision, morphing, swarming, 3D freedom, even invisible forces. But what happens when things go wrong? When robots encounter the unpredictable? When they fall, collide, face impacts? How do they survive and keep going?
That's a critical question, and it brings us to the concept of hyper-resilience. This isn't just about making robots strong. It's about designing machines that don't just passively withstand impacts, but can actively recover, adapt to damage, and continue functioning, ideally with minimal or no loss of performance.
So moving beyond just being robust.
Precisely. Traditionally, a lot of engineering design focused on achieving optimal performance under ideal conditions. Failure often meant catastrophic breakdown. But nature, as the source points out, shows a very different model. Animals fall, collide, endure harsh conditions almost daily, yet they often survive, adapt, heal. Think of the humble cockroach, apparently. It can withstand crushing forces up to 900 times its body weight and keep scurrying. Or how cats almost always land on their feet using their incredibly fast righting reflexes.
Right, they're built to survive tumbles.
Exactly. The biological lesson here is design for failure tolerance, not just for perfect performance under perfect conditions. Assume failure will happen and build in the capacity to handle it gracefully.
How do you design a robot to be hyper-resilient then? What are the principles?
Several key principles emerge. One is prioritizing flexibility over rigidity. Soft, compliant materials can absorb impact energy without breaking, whereas rigid frames tend to fracture. Flexible joints can deform under stress and then return to shape. This allows robots to survive impacts that would destroy a traditional rigid machine. Another is redundancy and modularity. Having multiple power sources, duplicate sensors, alternative control pathways, or modular limbs that can be jettisoned or replaced ensures that a single point of failure doesn't necessarily disable the entire system. And critically, self-righting and recovery mechanisms. Robots that can detect they've fallen or been damaged, and then initiate automated recovery sequences, maybe shifting their center of mass, using limbs to push off, inflating airbags, or even using controlled bouncing to dissipate impact energy and regain stability, essentially enabling them to pick themselves up, much like animals do.
What technologies make this possible?
Soft robotics is a huge enabler, using materials like elastomers or silicone that naturally deform and absorb shocks without permanent damage. Morphological computation is a fascinating idea, where the robot's physical shape and material properties themselves contribute to adaptation and control, reducing the reliance on complex computation. The body itself helps solve the problem of recovery. Dynamic gait adaptation allows legged robots to compensate in real time for damaged limbs or unexpected terrain changes, adjusting their walking pattern to maintain stability. And even self-healing materials are being developed, specialized polymers that can reform chemical bonds after being cut, or composites containing microcapsules of liquid metal that can flow to reconnect broken electrical circuits automatically.
Where are we seeing this applied?
Disaster rescue robots are a prime example. Robots inspired by snakes or cockroaches are being designed specifically to survive building collapses, navigate rubble, and withstand harsh environmental extremes. Space robotics, too, planetary rovers have to endure extreme temperatures, radiation, and rough landings, requiring significant resilience. Even areas like autonomous vehicles are exploring designs that can potentially survive minor crashes and continue operation, perhaps assessing their own damage and adapting driving behavior accordingly.
Philosophically, this really changes the idea of failure, doesn't it?
It absolutely does. In hyper-resilient robotics, failure isn't necessarily the end state. It becomes a temporary condition, maybe even an opportunity for adaptation. It's viewed as a normal part of operational life, something to be managed rather than simply avoided at all costs. It pushes us closer to the persistence and regeneration we see in living systems.
Okay, so robots can be strong, fast, adaptable, resilient. But can they be creative? Can movement itself be a form of expression for them?
That's the next frontier, and arguably one of the most profound. robotic creativity, where machines begin to use movement not simply for functional tasks, but to tell stories, evoke emotions, and express ideas. Movement as meaning.
How does that evolve from just, say, an industrial arm welding a car?
Well, historically, robotic movement was purely utilitarian, driven by efficiency and precision. Industrial arms followed pre-programmed paths. But advances in sensing, AI, actuation technologies, they've opened up vastly more possibilities. Robots now have degrees of freedom approaching biological organisms. Real-time adaptive algorithms allow for fluid, dynamic, less predictable movement. And crucially, artists, choreographers, and engineers are actively collaborating now to explore the expressive potential of machines designing movement for beauty, narrative, or emotional impact, not just productivity.
What are the components of expressive robotic movement? How do they speak through motion?
Several key components mirror human or animal expression. Posture and gesture are fundamental. The way a robot holds itself can communicate mood or intent. An upright, open posture might suggest confidence or welcome, while slumped, inward motions could convey sadness or hesitation. Timing and rhythm are incredibly important. Fast, sharp, staccato movements can energize or create tension, while slow, smooth, flowing motions might create calm or melancholy. The pacing shapes the emotional response, much like music. Spatial patterns also convey meaning how robots move in relation to each other or the environment. Approaching can suggest curiosity or aggression, depending on speed and posture. Circling might imply playfulness or threat. Moving together can show connection.
And this is leading to actual robotic performances, like dance.
Yes, robotic dance is a rapidly growing field. We're seeing humanoid robots performing synchronized routines, sometimes alongside human dancers. Quadrupedal robots, like Boston Dynamics Spot, have been choreographed into surprisingly balletic or playful performances. Swarm robots, especially drone swarms, are used to create these incredible aerial ballets, as we discussed. It's often a deep collaboration, with human dancers and choreographers working with roboticists to translate human emotion into robotic gestures or to design hybrid performances that explore the unique capabilities of both human and machine bodies, blurring the boundaries.
Beyond dance, what about other art forms?
Robotic creativity extends to painting and sculpture, too. Robots are being programmed to paint, sometimes using algorithms that generate brushstrokes based on simulated emotions or interpretations of music, creating abstract compositions born from movement patterns. They can also sculpt using robotic arms to precisely carve stone or wood based on digital designs, or even 3D printing complex forms layer by layer, sometimes directly in midair with specialized materials. Kinetic sculptures, where the movement itself is the art, are another key area.
And using movement to tell stories. Robotic narrative.
Absolutely. Movement can tell silent stories incredibly effectively. Imagine a robot reaching out hesitantly towards an object, then recoiling as if in fear. Or groups of robots moving in ways that suggest embrace, conflict, or support. Audiences naturally interpret these mechanical motions, projecting meaning and emotion onto them. Common themes emerging in robotic performance often echo timeless patterns of human storytelling: exploration, isolation, connection, conflict, transformation. The machine itself becomes a physical storyteller, expanding the language of narrative beyond words alone.
What tools are enabling this creative expression?
Specialized motion programming languages are being developed that allow choreographers or artists to define movements not just by coordinates, but by expressive qualities, specifying emotional tones, rhythmic patterns, or creating modular sequences that can be combined improvisationally. Machine learning plays a role, enabling robots to learn from human movement through imitation, or even to generate novel improvisational movements based on certain stylistic constraints or real-time inputs. Sensor integration is key for interactive pieces, allowing robots to respond dynamically to audiences, music, or other performers, making the storytelling more adaptive and engaging.
It all sounds amazing, but there must be challenges too.
Definitely. Achieving genuine emotional authenticity is hard, avoiding the uncanny valley, where movements seem almost human but slightly off, which can be unsettling. Technical limitations in hardware fluidity and responsiveness are still hurdles, and ethical considerations arise around authorship, attribution, who is the artist when a robot creates, and the potential for manipulation.
Okay, so with all this unprecedented motion, robots flying, swimming, morphing, swarming, dancing, creating, potentially even feeling resilient,
Yeah.
it brings us inevitably to the ethics. This new power clearly brings new responsibility and probably new dilemmas we've never really had to face before.
Absolutely. The source dedicates significant attention to the ethics of unprecedented motion. It argues that as robots gain these extraordinary capabilities, we enter a completely new moral landscape. How far should we push these boundaries? What limits must we respect? How do we balance the drive for innovation with fundamental values like privacy, safety, emotional health, and cultural preservation?
The source emphasizes that motion itself isn't neutral, right?
Not at all. Motion has inherent power. It commands attention. A sudden movement makes us look. It evokes emotion. A fast-approaching object triggers fear, while slow, gentle motion can soothe. It shapes perception. As robots gain increasing mastery over complex, expressive, and powerful movement, they gain an unprecedented ability to influence human emotion and behavior, whether intentionally or not. And as these moving machines enter our shared spaces, public areas, homes, workplaces, hospitals, their movement directly impacts not just physical safety, but also our emotional well-being and established social norms. The freedom of machine movement must be carefully weighed against the rights, dignity, and comfort of human beings sharing that space.
A huge issue must be privacy.
A massive one. Robots equipped with cameras, microphones, LiDAR, and other sensors can potentially collect vast amounts of data about us and our environments while they move around. Think about drones surveying neighborhoods, service robots monitoring activities inside homes, swarm robots mapping crowds and public spaces. When motion becomes mobile surveillance, privacy is inherently at risk. The source stresses that informed consent is crucial. Individuals should have the right to know when they are being observed by moving machines, how that data will be used, and ideally have the ability to opt out or control data collection. Ethical motion systems must be designed with privacy preservation in mind, perhaps through data anonymization, onboard processing to minimize raw data transmission, and strict limits on data retention. Motion should serve human needs, not become a tool for pervasive surveillance.
And then there's safety and trust, both physical and maybe emotional.
Exactly. Physical safety is the obvious starting point. Moving machines, especially large, fast, or powerful ones, pose inherent risks. Collision injuries, falling debris from aerial robots, malfunctions causing unpredictable behavior. Designing for safety involves redundant control systems, fail-safes, soft robot designs where appropriate, predictable motion patterns, and clear signaling of intent. But beyond the physical, there's emotional and psychological safety. The way robots move can significantly impact how we feel around them. Aggressive or unpredictable movements can cause fear or anxiety. Even overly expressive robots could lead to unhealthy overattachment or unrealistic expectations. Designers need to consider emotional ergonomics, how robot motion affects human feelings, and aim for designs that foster trust and comfort, not unease.
That ties into the whole emotional impact of robotic motion. You mentioned attachment.
Yes, it's complex. Humans have a natural tendency to anthropomorphize, to attribute human-like qualities and emotions to non-human things, especially things that move in seemingly intentional ways. This can lead to strong emotional attachment to robots, like robotic pets or social companions. While this can have benefits, like reducing loneliness, the source warns of risks, potential for emotional manipulation, robots designed to elicit specific responses for commercial or other purposes, unhealthy dependency, or even grief when a robot malfunctions or is replaced. There's also the question of emotional authenticity. Should robots be designed to mimic emotions they don't actually possess? Ethical guidelines are needed to govern how emotional bonds are designed and managed, prioritizing genuine connection and avoiding deception. Trust is built on authenticity.
How might all this new machine motion change our culture?
Profoundly, potentially. The source suggests several cultural shifts. Our concepts of work and play could change dramatically as robots take on more physical tasks and perhaps even become partners in creative or athletic pursuits. Our very definitions of beauty and expression might expand to include new forms of kinetic art or robotic performance. And there's a need for sensitivity around the preservation of cultural identity. As robots are deployed globally, their movements and interactions must respect diverse cultural norms and values. For example, gestures considered friendly in one culture might be offensive in another. Design needs to be culturally aware and ideally involve input from the communities where robots will operate.
So how do we navigate all this ethically? What frameworks can guide us?
The source proposes several key ethical frameworks. Human-centered design. Always prioritizing human safety, dignity, autonomy, and overall well-being in the design and deployment of moving robots. Transparency. Being clear and honest about what robots can do, what data they collect, how they make decisions, especially regarding movement, and signaling their status and intentions clearly through visible cues or communication. Accountability. Establishing clear lines of responsibility for the actions of robots, including mechanisms for redress if harm occurs. This involves legal frameworks, but also design choices that facilitate logging and auditing. inclusivity, ensuring that robotic motion technologies are designed to be accessible and beneficial to diverse populations, avoiding bias, and actively involving affected communities in the design and governance processes.
Can you give an example scenario?
Sure. Consider drones in public spaces. Ethics requires balancing surveillance utility, for example, traffic monitoring, with privacy rights, avoiding facial recognition, minimizing data retention. Safety means robust collision avoidance and clear flight paths. Transparency means making drones easily identifiable and their purpose known. Or emotional robots in healthcare for the elderly. Ethics demands ensuring genuine benefit, avoiding manipulation or replacing human contact entirely, managing attachment responsibly, and ensuring patient autonomy and data privacy.
Sounds incredibly complex to govern, especially with technology changing so fast.
It is. The source acknowledges major challenges in ethical governance. The rapid pace of technological change often outstrips our ability to create effective regulations. The global diversity of values makes universal standards difficult. And the law of unintended consequences means even well-intentioned designs can have negative effects. The path forward likely involves ongoing robotic ethics education for engineers and the public, participatory design models that bring diverse voices into the development process, potentially ethical certification standards for robotic systems, and crucially, continuous global dialogue and collaboration on these shared challenges.
So the ultimate goal is motion with meaning.
Motion with meaning and motion with responsibility. As machines learn to move with unprecedented grace, power, and even emotional resonance, we must move thoughtfully too. We need to proactively craft a culture and ethical framework where innovation serves humanity. Robotic motion must be guided by principles that honor life, respect diversity, nurture trust, and empower creativity for everyone.
Wow. Okay, this deep dive has truly taken us on quite a journey. From the inherent limits of our own human movement, fascinating in itself, all the way to the seemingly boundless possibilities of robotic motion. We've talked about morphing machines that can stretch and flow, swarms coordinating like a single mind, invisible forces moving matter without touch. It's incredible stuff. And threaded through it all, these profound ethical questions that inevitably emerge when we start to redefine the very concept of movement itself.
And it seems clear, doesn't it, that the future isn't really about robots simply replacing us or us versus them. It's much more likely to be about a deep partnership. Humans and robots co-creating a dynamic world, inhabiting shared physical spaces, workplaces, homes, cities, in ways we're only just beginning to imagine. It points towards ecosystems of collaboration, really, not segregation.
And it sounds like a partnership built on complementary capabilities.
Exactly. Humans bring creativity, emotion, intuition, contextual understanding. Robots offer tireless precision, superhuman strength and endurance, operation in extreme environments, adaptation across incredible scales. Imagine those medical micro-robots assisting surgeons with nanoscopic precision, but guided by the surgeon's experience and artistry. Or vast construction swarms shaping structures according to human aesthetic vision and architectural ingenuity. We'll be able to achieve things far beyond what either humans or robots could do alone.
Which implies a co-evolution of motion languages.
I think so. Robots won't just copy us. We, too, will inevitably learn to interact and maybe even dance with these new forms of motion. We might develop new gestures specifically to communicate with flying drones or service robots. New athletic forms could emerge, blending exoskeleton-enhanced power with organic human agility. We might even find new ways to express and perceive emotion through dynamic interactions with sophisticated robotic companions. Motion itself becomes a shared, evolving language between species, in a way.
And this could lead to a kind of cultural blossoming centered around shared motion.
That's a beautiful way to put it. The source envisions new art forms emerging, maybe hybrid ballets where aerial swarms interact with human dancers to create kinetic symphonies across entire theaters, or dynamic public sculptures constantly reshaped by environmental data or human interaction via robotic elements. We might even see new rituals or celebrations involving robotic participants, robotic musicians playing alongside human orchestras maybe, or public plazas becoming living canvases of interactive kinetic light and form. Perhaps even shared mythologies might arise about these moving machines.
And the emotional landscape changes too.
Profoundly. Co-motion fosters connection. Think about trust developing through reliable interaction, empathy arising from perceived robotic expression. Issues of attachment and identity will become more complex kinetic learning robots for children, adaptable companions for the elderly, providing physical and emotional support through movement. Emotional resonance achieved purely through shared motion, expressing joy, grief, or playfulness without words. This raises an important question, maybe a concluding thought from the source material. The greatest dance humanity performs. You won't be alone. It will be with the machines we create.
The greatest cats.
Imagine cities that almost literally sing and dance, traffic flows optimized like symphonies, buildings subtly morphing in response to weather or occupancy. Or think further out, interplanetary motion symphonies, where human-robot teams craft kinetic art on alien landscapes, maybe perform zero-gravity ballets in space stations. Movement becomes this shared language, teaching each other things words cannot, expressing complex ideas and emotions, ultimately choreographing a civilization towards greater meaning, beauty, and perhaps even transcendence.
So what does this all mean for you, our listener, taking all this in? Perhaps it just means looking at every moving object a little differently from now on, wondering what new language it might eventually speak, or what currently unimaginable dream it might someday help create. The future, it seems, is very much in motion. And that motion is truly beyond ourselves.